Good morning to all. In the previous tutorial, we saw the fluid as a continuous medium, and we can define the properties of the fluid like density and viscosity in every point in the continuous medium in an average sense. We also saw that fluid mechanics is a branch of continuum mechanics, and the continuum mechanics are governed by law of conservations. Today we see the field of continuum mechanics includes solid mechanics, fluid mechanics, and thermodynamics. The difference between the solid mechanics and the fluid mechanics is the choice of the reference frame. As solids deforms by a very small amount, it is possible to follow the fixed collection of materials of the solid as it evolves in time. So this is termed as a Lagrangian reference frame. For fluid mechanics, the motion of the fluids or the movement of the materials is too great to keep track of a fixed collections, and therefore it is simpler to observe the flow of those fluids past a fixed reference frame termed as control volume. This type of study is termed as Eulerian reference frame. Solid mechanics attempts to model the stress and strain of a material. The solid mechanics concept of stress was developed by Euler and Bernoulli with the notion of stress tensor, and finally formalized by Cauchy in 1823. The field of thermodynamics was developed during the industrial revolutions in order to quantify the interplay between heat and work. It provides the continuum notions or the continuum definition of temperature, pressure, and entropy. The entire formulation of thermodynamics assumes a fluid at thermodynamic equilibrium, which significantly limits the applicability of thermodynamics. Now, the continuous fluid dynamics model the flow of fluids away from a hydrodynamic equilibrium, typically for phenomena acting at large time and large length scale than required for a thermodynamic equilibrium. These continuum fluid dynamics models are governed by Navier-Stokes equations. This Navier-Stokes equation is formulated independently by Navier in 1822 and Stokes in 1845. This Navier-Stokes equation represents a continuum implementation of Newton's law with a variety of closer assumptions. For example, the solid mechanics stress tensor defined in Navier-Stokes equations is often replaced by a scalar dynamic, hydrodynamic pressure, a shear viscosity, and in some cases a bulk viscosity. Although the analytical solutions of these Navier-Stokes equations, which are represented in mathematical terms as nonlinear partial differential equations, is impossible for complex flow conditions. With the advent of supercomputers, numerical solutions can be possible, especially to study the chaotic behavior of fluid flows, a phenomena known in fluid mechanics terminology as turbulence. Thank you.